In this video, we're going to go over some practice problems from sections 12.1, 12.3, and 12.4 from our textbook. So starting with section 12.1 here, for questions 21 and 36, we want to write the center radius form of these circles and then graph them. So for question 21 here, this one's fairly simple and we've done this before. We're going to use the fact that the equation for a circle is given in standard form like this here. So we're going to have x minus a squared plus y minus b squared. It's going to be equal to our radius squared, where a and b are going to be the x and y coordinates for the center of our circle. So with this in mind here, and given that the center of the circle is this and the radius is 3, we can write this guy in center radius form like this here. So this will be the same thing as x plus 3 squared plus y minus 2 squared, and this is going to be equal to 3 squared or 9. Now I just want to be careful, since this formula does already have this minus sign here. If either one of these coordinates here are negative, when we input a negative into this formula, it's going to make this a positive. So that's why we have this x plus 3 and then this y minus 2 here. Now what we can do is graph this guy, and we know how to do that. The first thing we're going to do is graph our center. So that'll be negative 3, 2. So graphing that on this graph here is going to be that point. Now what we're going to do is just move 3 units in every single direction of this point here. So we're going to move 3 units this way, this way, this way, and there. So then we can graph our circle by just connecting these points here, and then with the iPad that'll make a nice circle there. Alright, so that's how we would graph question 21 there. Now for question 36, we again want to write this guy in center radius form and then graph it. But this one is a little more complex here. What we're going to do in order to write this in our center radius form is we're going to complete the square. Remember, the whole point of completing the square is to try to rewrite an equation to be a perfect square trinomial so that we can factor it. We know perfect square trinomials have this form here, where we have x minus a squared, and this is going to be equal to, for example, x squared minus 2ax plus a squared. This is a perfect square trinomial. So what we want to do is try to rewrite these guys here as a perfect square trinomial so that we have this square term, which is this first term here, for our center radius form of our circle. Now notice for this one, we have an x squared and a y squared. That kind of tells us that this is going to be a circle, and what we're going to have to do is try to complete the square in one variable x and in the other variable y. We're going to try to complete the square so we get this out of our x terms, but we also want this y minus b here out of our y terms so that we can write this in center radius form and graph it, just like we saw in the last example. So in order to complete the square here, we're going to follow the same procedure that we've seen before. The first thing that we're going to do is move the constant terms to one side of our equation and keep the variable terms on one side. And we're also going to kind of group the x variables together and the y variables together. So we have x squared plus 8x. Then we're going to have plus y squared plus 2y. And then moving this negative 8 to the other side of our equation is going to make this a positive 8. Now the reason why we have this space here is because when we complete the square, we're going to have to add a certain quantity to both sides of our equation. And that quantity is given by looking at this here. It's going to be that minus b over 2a squared quantity here. Now in this case, b is going to be 8, so we're going to have a minus 8 over 2 times a, which is 1. So this is going to end up being negative 4 squared, which gives us a positive 16. So in x here, we're going to have to add a positive 16 to both sides of our equation. Now doing the same thing, but now for our y variables here, we want to figure out what this quantity is that we're going to add to both sides of our equation. Plugging this into this formula here, we're going to get that that quantity is 1. So we're going to add 1 to both sides of our equation. From here, looking at the first 3 terms here, we have a perfect square trinomial in our variable x, and then these 3 terms here are a perfect square trinomial in our variable y. So we can easily factor these guys. This first perfect square trinomial is going to end up being x plus 4 squared. And then the second one here is going to be y plus 1 squared. So that's what we have on the left-hand side of our equation. And then on the right-hand side of our equation, we have 8 plus 16 plus 1. So this is going to give us 25. So we have an equation in center radius form. In this case, our center is going to be negative 4 comma negative 1. Since we have these guys are positive here, the coordinates must both be negative. And then our radius in this case is going to be the square root of what we have on the right hand side, since in our center radius form, our radius is squared here. So in this case, our radius is going to be 5. So we can graph this with this information here. If our center is negative 4 comma negative 1, that's going to be right there. And then using the fact that our radius is 5, we're going to move 1, 2, 3, 4, 5 units up and in every direction. So there, here, and here. Now we can connect these dots here to make our circle. Might just be a rough sketch, but the iPad does make it a little bit nicer. Okay, there we go. Now, for the next two questions here, we're going to be graphing ellipses. Now, the standard form for an equation of an ellipses is given by this here. We're going to have x minus h squared over a squared plus y minus k squared over b squared, where our h and k here is going to be the x and y coordinates of the center of our ellipses. And this is always going to be equal to 1. Now, looking at this first question here, question 46, we have an ellipses here in its standard form. Now, since we don't have this minus h or k here, we just have x squared and y squared by itself. What this tells us is that the center of this ellipses is going to be 0, 0, which is the origin. So our h and our k coordinates are both 0. Now, what's nice about this ellipses as well is that our x and y intercepts are given by our a and b values here in our standard form. So our x-intercepts are going to be the plus or minus of our a value, comma 0, and then our y-intercepts is going to be 0, comma plus or minus our b values in our equation. Now, going back to our original equation here, this is going to be the same thing as x squared over 3 squared plus y squared over 2 squared, which is equal to 1. So in this case, looking back at our standard form for an ellipses, this means our a value is going to be 3 and our b value is going to be 2. So our x-intercepts here are going to be plus or minus 3. So negative 3 comma 0 and positive 3 comma 0. And then our y-intercepts are going to be 0 comma negative 2 and 0 comma positive 2. So we can use these 4 points here and the fact that our center is going to be at the origin to graph this ellipses. So our first point is going to be our center. Then we're going to graph our two x-intercepts. That's going to be negative 3 comma 0 and 3 comma 0. And then our y-intercepts are going to be here. So 0 comma negative 2 and 0 comma 2. Now to graph this ellipses here, we're just going to connect all of these points. And so that's what we'll get here. All right, so for question 53, we again want to graph this ellipses here. Now this one's slightly different from the last example that we saw in that the center of this guy is not going to be the origin. The center is going to be given by this 2 and this 1 here. Looking back at our standard form for an equation for an ellipses, our h comma k are our x and y coordinates of the center of our ellipses. So the center is going to be given by 2 comma 1. Now this is also going to affect our x and y intercepts. We saw in the last example that the x and y intercepts were given by our a and b values. So in this case, our a value is 4, since 4 squared is 16, and our b value is going to be 3, since 3 squared is 9. So in the last example, this would have represented our x and then our y coordinates for our x and y intercepts. Now, in this case, the easiest way to think about an ellipses that doesn't have the center at its origin is starting with an original ellipses that would be centered at the origin and then shifting that guy. So that's exactly what we're going to do here, and I'm just going to write this out in words here. So this is going to be an ellipses with center at the origin, so that would be 0, 0. And in this case, if we just pretend it's at the origin for a minute, we're going to give our x and y intercepts. So our x-intercept would then be, or x-intercepts would be plus or minus 4, 0, and then our y-intercepts are going to be 0, plus or minus 3. Okay, so just bear with me. That's how we're going to think about this for a second. That's how we would find our x and y intercepts given our a and b values if this was an ellipses centered at the origin. However, what's going to change is that we're going to take these 5 points here and we're going to shift them based off of this center here. So this is going to be an ellipses with center at the origin and x and y intercepts here. That's going to be shifted 2 units to the right, since our x value here is positive 2, and 1 unit up since our y value is positive 1. So it's exactly what we have here. The center of this guy is going to be 2, 1, so that point. So this means if we started out with an ellipses centered at the origin, we're going here and we're shifting 1, 2 units to the right and 1 unit up. So that's what we did with our origin point, this 0, 0 here. So let's just do the same thing for our x and y intercepts. Our original x-intercept, one of them would be negative 4, 0 if we were centered at the origin. So that would be right around here. But we know this is an ellipses shifted 2 units to the right and 1 unit up. So 1, 2, and then up 1. So this would be our next point. Now doing the same thing with our other x-intercept, that would be positive 4, 0. We're going to shift 1, 2 units to the right and up 1. We can do the same thing with our y-intercepts. 0 plus or minus 3 is going to be here and here, but we're going to shift these guys 2 units to the right and up 1. So that'll be one of them. And the last one is going to be here. So now those are the 5 points for this ellipses here. And then that's how we would graph it here. So that's the process that we can use when an ellipses is not centered at the origin here. Another way to think about it is just adding this quantity 2 to all of our x values here, and then adding this quantity 1 to all of our y values for these coordinates here. So same idea here. I just like to start with an ellipses centered at the origin and then shift it. All right, this brings us to section 12.3. Now in this section, we're going to be solving systems of equations. Now we saw in previous sections solving systems of linear equations using our substitution and elimination method. Now we're going to be doing the same thing in this section, but now we're going to be dealing with quadratic equations. We're no longer just looking at linear equations. So that's the difference here. Now for question 15, we want to solve this system here using our substitution method. So very similar to what we saw in previous sections here when we were dealing with linear equations. What we're going to do is substitute one value of a variable into the other. So for example, we already have that y is equal to x squared plus 6x plus 9. And then our second equation says that we have x plus y is equal to 3. So what we can do is just plug in this value for y into this guy. So doing that, we're going to be left with an equation in just one variable x, and then we can easily solve it using the methods that we've learned in the last several sections. So we're going to have x plus our y value, which is x squared plus 6x plus 9. And this is going to be equal to 3. So again, just to emphasize, we're just plugging in that y value. Now what we can do is combine like terms and see if we can solve this guy. So we're going to have x squared plus 7x, so combining this x and this x term here, and then we're going to subtract 3 on both sides of our equation. So we're going to be left with plus 6 here as our last term, and then 0 on the right-hand side. Now we can easily factor this guy. This is just going to be x plus 6 times x plus 1. That'll give us 0, and so we have two solutions here. This will be negative 6 and negative 1. So now what we need to do is we need to plug both of these solutions here into one of these equations here and solve for y. So we are going to have two different solutions here. Now the easiest way to do that would actually be to work with this second equation here, because if we rearrange this and solve for y, we're going to get that y is equal to 3 minus x. So using this, we can just plug in the values for x that we found into this here and see what we get for y. So remember, we found two different values. So let's first plug in -6. So if we plug in -6, we're going to get y is equal to 3 minus -6, which gives us a positive 9. Now let's plug in our -1. We're going to do the same thing. We're going to get positive 4. So that means our solution set in this case is going to consist of two solutions. The first one being -6, 9. And the other one is going to be -1, 4. All right, so this would be our solution set here. Now for the next example, question 33, we're again going to be solving a system of equations here, and these guys are both quadratic equations, but we want to do so using our elimination method. So just like we saw in previous sections, the point of that is to add these two systems of equations together in a strategic way so that one of the variables cancels out. Now, what we're going to do is, let's try to cancel out our y squared variables. Notice that we have 3y squared and 3y squared in the top and bottom equation here. So if I were to multiply both sides of this bottom equation by a -1 here, what happens is the new system, it's going to be unchanged since I did it to both sides of our equation, but we're going to end up with -x squared minus 3y squared is equal to -3. So now, when I go to add these guys together, what happens is our variable, or our y squared terms are going to cancel out. Now, something I just want to point out here is that we could have chose a different path. We could have chosen, for example, to eliminate our x squared terms, and we could have multiplied this guy by a -2. Okay? We could have also multiplied this one by a negative. It doesn't matter, as long as you follow the math correctly, you'll end up with the correct answer. Now for this one, eliminating our squared terms, we're going to end up with, we're going to have 2x squared minus x squared, which just gives us a positive x squared. It's going to be equal to positive 3. So x is going to be equal to plus or minus the square root of 3. So with this, we again have two x values, and we want to see what our two y values are going to be. So let's pick this bottom equation again. This one's going to be a little bit easier to solve for y here because we don't have a coefficient for this x squared term. So when we plug in our square root 3, we're going to get a nice number. So we're going to use this guy, and then we're going to plug in our values for x into here. So we're to plug in the square root of 3 into x squared. We're going to end up with this here. Now we know the square root and the square here is going to cancel each other out. So we're just going to have 3 plus 3y squared gives us 3. Now we can solve for y by first subtracting 3 on both sides of our equation. We're going to end up with 3y squared is equal to 0. And then we want to divide both sides by 3. We still end up with y squared gives us 0. So solving for y, we're going to get 0. Now as you may have guessed, the same thing's going to happen if we were to plug in a negative square root of 3, because we know that a negative value squared is going to give us a positive value. So we're going to get the same thing here. We'll have 3 plus 3y squared gives us positive 3. So following the same steps here, we're going to end up with y is equal to 0. So in this case, our solution set is going to consist again of two solutions here. We're going to have, and I'm going to write this with our plus or minus notation. So we're going to have plus or minus the square root of 3, and for both of those, our output is 0. So this is our solution set for this guy. Now for this last question in this section, we're going to be again solving a system of equations, but in this case, we're going to have to use a combination of methods to do so. So the first thing that we're going to do is try to get rid of one of our squared terms. We got a lot going on here. Let's see if we can reduce this in any way. Now, just like in the last example, if I were to multiply both sides of this top equation here by a -1, we're not going to change the system of equations, but we're going to end up with this here. And then our bottom equation is going to stay the same. Now, if we were to add these guys together, so using our elimination method, notice that our x squared terms are going to cancel, which is nice, that's what we wanted, but our y squared terms are also going to cancel. So this reduces nicely. We're just going to be left with that x times y term here, and this is going to be equal to negative 11 plus 3, so negative 3. So from here, we're just going to solve for one of our variables. Let's solve for y. Doing that, we're going to get y is equal to negative 3 over x. And from here, that's where our substitution method is going to come into play. So if y is equal to minus 3 over x, what we can do is substitute this y value back into one of our equations and get an equation just in terms of x and solve for that guy. So what we're going to do then, let's plug in this value for y into this value for y here. And we're going to choose this one because obviously this equation is a little less complicated than the one on top. All right, so don't want to run out of room here, so let's do it up here. So we're going to plug in this value for y into our bottom equation. So we're going to have x squared minus y squared, so that'll be negative 3 over x squared, and this is going to be equal to 8. All right, now we want to get rid of, actually the first thing that we have to do is distribute this square to both of these guys. So we're going to have x squared minus, this will give us a 9 over x squared, and this is equal to 8. So from here we have an x squared in our denominator, and usually we want to clear fractions. So the first thing that we're going to do then is actually multiply both sides of our equation by x squared. Doing that, we're going to end up with, we're going to have x squared times x squared. This is an arrow here. So that first term is going to be x to the 4th power, and then we have x squared times this guy. So just to emphasize, we're going to have x squared times this 9 over x squared, and as you can see, these guys are going to cancel. So we're going to be left with x to the 4th minus 9 is equal to 8x squared. So now this is looking like an equation that we might be able to solve. Let's move all of our variable terms to one side. We're going to have x to the 4th minus 8x squared minus 9 is going to give us 0. Now from here, we're not exactly sure how to solve an equation that has degree 4. However, we can use our substitution that we saw a few sections ago. If I were to introduce a new variable, let's say u, and I let u be equal to x squared, I can substitute this u back into this equation here where necessary. So if u is equal to x squared, this first term here can be written as u squared. So I'm going to have u squared minus, I have 8 times x squared, but remember x squared is u, so minus 8u minus 9 gives us 0. Now from here we can easily factor this. This is going to be u minus 9 times u plus 1, which gives us 0. Now we don't know exactly what this is going to be. Well, this is going to be u is equal to positive 9 and u is equal to negative 1. However, we're trying to solve for x. U is equal to x squared. So what we're going to do from here is substitute this x squared back into this u value. So we're going to get that x squared minus 9 times x squared plus 1 gives us 0. So now from here we can figure out what our x values are going to be. So this is going to be, x squared is going to be equal to 9, and then x squared is going to be equal to negative 1. So ultimately, we're going to get that x is going to be equal to plus or minus 3, and then x is going to be equal to plus or minus I. Remember, if we're going to take the square root of negative 1, that's going to give us I. So we already have 4 different x values here. So what we're going to need to do is plug in all 4 of these x values into one of these equations here and get 4 different y values. So going back to this equation here, though, we already solved for y in terms of x. So y is equal to minus 3 over x. So let's actually just use this equation to figure out what our y values are going to be. That's going to be much easier. So let's do that up here. For x is equal to negative 3, let's see what our y value is going to be. Y is going to be negative 3 over x, which is negative 3. So this is going to give us a positive 1. Now looking at positive 3, y is going to be negative 3 over 3, which gives us a negative 1. Now when x is equal to negative I, we're going to get y is equal to negative 3 over negative I, which is just going to give us a positive 3 over I. And then when x is equal to positive I, we're going to get the negative version of this. We have negative 3 over positive I, which is going to give us negative 3 over I. So these are the 4 y values, which correspond to our 4 x values here. So we're going to have 4 solutions in our solution set. So this can be written as, when we have a negative 3, we're going to get a positive 1. When we have a 3, we're going to get a negative 1. When we have a negative I, we're going to get 3 over I. And then when we have a positive I, we're going to get negative 3 over I. So these would be our solutions in our solution set. Let's move this over so we can use our set notation. Alright, so these would be our 4 solutions for this one. Alright, so for this last section, section 12.4 here, we're going to be graphing inequalities. So starting with question 19 here, we want to graph this guy. Now notice we have an inequality with 2 variables that are both squared. So that tells me this might be a circle or an ellipses. But notice we have a coefficient in front of one of our squared terms, so I'm leaning more towards ellipses. So what we're going to try to do is first write this in the standard form of an ellipses. So let's do it on the side here. We're going to have x squared minus 4 is greater than or equal to negative 4y squared. So if I want to write this in our standard form, the first thing that I'm going to need to do is have all of our variable terms on one side and then our number on the other. So I'm going to add 4y squared to both sides of this inequality. And I'm also going to add 4 to both sides. So just switching those guys around, we're going to have x squared plus 4y squared is going to be greater than or equal to 4. Now this is starting to look like the standard equation here. However, we know that we need to have 1 on the right-hand side. So what we're going to do then is divide both sides of this inequality here by 4 so that we're left with 1 on the right-hand side so that it's in the standard form for an equation for an ellipse. So we're going to divide this by 4, and whatever we do to one side, we have to do to the other. So we're going to have x squared over 4 plus, we're going to have 4y squared over 4, which just gives us y squared, and this is going to be equal to 1. Now notice this is in the standard form for an equation for an ellipse here. And sorry, we have a greater than or equal to sign here. So our first step is writing this guy in standard form. Now the next step is figuring out our boundary, because what we're trying to do is find solutions that'll make this statement true. Find x and y values such that when we plug them into the left-hand side here, they are going to be greater than or equal to 1. Now in order to do that, we're first going to identify our boundary and graph it, and then figure out where our solutions lie. So the boundary is then just going to be this equation here. So we're getting rid of that inequality sign. And I'm actually going to write this as y squared over 1 just to emphasize that this is in the standard form of an ellipse. So this is our boundary. We want to graph this guy. We know how to do that from the last section here. Our x-intercepts is going to be plus or minus the square root of this guy. So plus or minus 2 comma 0. And then our y-intercepts is going to be 0 comma plus or minus the square root of our b value, our 1 here. And then we also know that the center of this ellipse is going to be the origin. Since we have just x squared and y squared here, we don't have our h or k coordinates. So our center is given by this, and we're just going to plot our x and our y intercepts. So we have a small ellipses that looks like this here. All right. Now from here, we want to figure out if our solutions lie within this ellipses or on the outside of it. Now we can do that by picking a test point. Now the easiest test point to pick would just be the origin that's right in there. we're going to plug in 0, 0 into our equation here. So we're going to have 0 squared over 4 plus 0 squared over 1, and we want to see if this is greater than or equal to 1. That's what we have here, this equation. Now, obviously, this is not going to be greater than or equal to 1, so this is a false statement. So that means our solutions are not going to lie inside of this ellipses, but they're going to lie on the outside of it. So everywhere but, let's do that nicer, everywhere but on the inside of this guy. So we're just going to shade this region here to emphasize this. So we could write that our solutions lay on the outside of this ellipses. All right, and then something else to note here, whenever we are solving these inequalities by graphing, we usually use a solid dotted line to say that the boundary is included. So as you can see, going back to this inequality here, we want to figure out which values will make this greater than or equal to 1. So all of the values on this boundary of the ellipses will satisfy this. So going back to this here, we'll say solutions lie on the outside of the ellipses and include the boundary, which is what we graphed, which is what we have here. All right, so let's look at our next question here. So we're again going to be graphing. Now we're graphing a system of two equations. And these are both linear equations, so we can easily graph them. And in order to do that, I'm actually going to write both of these in y is equal to mx plus b form so that we can easily graph them. So let's do that down here. You could also pick different input and output values if you wanted, or different input values to see what is outputted to graph this. But in this case here, I'm just going to try to write this in y is equal to mx plus b form. So in order to do that, I'm going to move 2x to the other side of this inequality and then divide by 5. So I'm going to get y is less than 10 minus 2x over 5. Now, this is going to simplify to minus 2 over 5x plus 2. So now this is in y is equal to mx plus b form, so I can easily see what my slope and y-intercept is. Now, in terms of solving this problem here, this is now going to become our boundary equation. We're going to have y is equal to minus 2 over 5x plus 2. Now we're going to do the same thing for the other equation in this system. We have x minus 2y is less than 4. So again, let's write this in our mx plus b form. So we're going to have minus 2y is less than 4 minus x. And we want to be careful with this one. Remember when we want to solve for y here, we're going to divide both sides of this inequality by -2. And whenever we're dividing or multiplying by a negative with these inequalities, it's actually going to change this sign here. It's going to give us the opposite of this guy. So if we divide by a -2, we're actually going to get that y is greater than 4 minus x divided by this -2. So we always need to flip this sign here if we're multiplying or dividing by a negative. So this is going to give us that y is going to be greater than, our m here is going to be 1/2 because we have minus x divided by -2. That'll give us a positive value, and then the coefficient in front of this x here is 1, so we're going to have 1/2 x. And then we're going to have 4 divided by -2, so that'll give us a -2. All right, and then again, in terms of this problem here, we want to figure out what our boundary equation is. So we're going to have 1/2 x minus 2. So from here, what we need to do is graph these guys, and we're going to do some color coding here. And the solutions are going to lie in the intersection of these two inequality values, or these two inequalities. So let's graph these guys. In blue, we're going to graph our first boundary equation here, the -2 over 5x plus 2. So that plus 2 tells us that our y-intercept is going to be 2, 0. And then our slope is negative, so our line is going to be in this direction here. Our rise is going to be -2, and our run is 5. So if our rise is -2, that means we're going to go down 2 units, and then we're going to go to the right 5 units. So right here, so down 2 and to the right 5. Now repeating this process in this region here, we can kind of switch it. So instead of going down 2, we can go up 2, but in this case, to keep that negative, we have to go left 5. So that'll be this here, and then repeating this, we have this here. Now, before I graph this, I just want to emphasize that we're trying to find values that'll satisfy this, but we don't have an or equal to sign here. So that means all of our values on these boundary lines are not going to be included in our solution set. So in order to emphasize that, we're going to draw our boundary line with a dashed line, just to emphasize that we're not including the points on this boundary line. It's kind of similar to how we use parentheses and brackets to emphasize if solutions are included or not. All right, let's do the same thing for this other boundary equation here. Our y-intercept is going to be this -2 here. Then our slope is going to be up 1 over 2, and we have a positive slope. So these are going to be some points here on this line, like this. Now, again, just to emphasize, we're not going to be including the points on this boundary line, so we're going to use a dashed line. Now, the next thing we want to do is figure out what solutions are going to satisfy these inequalities here. We want to find y values that are going to be less than this line, this equation that we have. Or I guess it wouldn't be an equation in this case since we have this inequality. But we want to figure out which y values are going to be less than this line here in blue. So we're going to shade this in blue. All of the y values below this dashed line are going to satisfy this. They're going to be less than this guy. We can see this graphically, and we can also pick any test points in this region, and we're going to find that this is true. Now, similarly, for this other inequality here, we want to now find all the y values that are bigger than this line here. So, keeping with our color coding here, we're going to shade everything above that line. All of these y values here are bigger than this green line here. Now, our solutions are going to lie in the intersection of these two regions here, so everything in dark green. So we'll write that on this side here. So our solutions are going to lie in the intersection of these two inequalities. All right, so for the last question in this section here, we're going to be graphing inequalities just like we saw in the last several examples here, but we're going to do that so that we can find a maximum value. So we're told that the Schwab Company designs sells 2 types of rings, the VIP and the SST. The company can produce up to 24 rings each day and up to 60 hours total of labor. Now, we know that it takes 3 hours to make one VIP ring and 2 hours to make one SST. We're also given the profit for each of them. Now, with this information, we're going to be able to figure out how many of each type of ring should be made daily to maximize this profit and what that maximum profit is. So the first thing that we're going to want to do is assign these rings to variables to make our lives a little bit easier here. Let's let x be equal to our VIP ring, and then y be equal to the SST ring. Now from here, we're going to set up equations and inequalities based off of the information given in this word problem. So, for example here, we're told that the profit for one VIP ring is $30 and one SST is $40. So this means the profit, which we're going to call P, is going to be equal to 30 times the number of VIP rings that we make, plus 40 times the number of SST rings. Similarly, we're also given information to set up an inequality here. We're told that we can produce, or the company can produce up to 24 rings each day. So let's stick with our color coding here. That means the amount of VIP plus the amount of SST rings can't exceed 24 rings. So this has to be less than or equal to 24 because we can make 24 rings. Now this last piece of information here, we're told that in terms of labor, it takes 3 hours to make one VIP and 2 to make one SST ring, and the total hours of labor is not going to exceed 60. So we can set up again another inequality with this information. So we're going to have 3 hours to make one VIP plus 2 to make one SST is not going to exceed 60 hours. Now, something else that we have to keep in mind when we are dealing with these applied problems is the context. So since we are talking about the quantity of rings here, let's just put this on the side. Our rings can't be negative. We can't make a negative amount of rings. So our x and y's can't be negative. So this is going to be another constraint or another inequality that we have. Our x is going to be greater than or equal to 0 because we could produce 0 rings, 0 VIP rings. And similarly, we're going to have y is greater than or equal to 0 because we could also produce 0 SST rings. So from here, what we're going to want to do is graph all 4 of these inequalities here. Now, in order to do so, for the first 2 inequalities, let's try to write this in a nicer form. I'm going to try to write this in mx plus b form. So for this first equation or inequality here, we have x plus y is less than or equal to 24. So if I subtract x on both sides here, I'm going to get y is less than or equal to 24 minus x. Then writing this in mx plus b form, y is going to be less than or equal to minus x plus 24. Then this equation here is going to be our boundary. So our boundary is going to be y is equal to minus x plus 24. So what we're going to do is graph this line here. Now similarly, we're going to do the same thing with this second inequality here. We're going to want to try to write this in mx plus b form. So we're going to subtract 3x on both sides of this inequality and then divide by 2 to get y completely alone. So we're going to have y is going to be less than or equal to 60 minus 3x. Then we're dividing that by 2. So in our mx plus b form, this is going to be negative 3 over 2x plus 30, since we're doing 60 divided by 2. Now our boundary then, in this case, is going to be the equation that y is equal to this guy here. So now what we can do is graph both of these lines here and the boundaries for these guys. So our boundaries for both of these inequalities would be x is equal to 0 and y is equal to 0. So let's do that first. We'll do that in black here. This is going to be x is equal to 0. To 0. And then on the x-axis here, we're going to have that y is equal to 0. Now the next thing we want to do is graph these 2 lines here. So in green, we're going to have minus x plus 24. So this means our y-intercept here is going to be at 24. And notice this graph here is going to be increasing in increments of 2. So 24 would be that point here. So we have this. Now our slope is negative, and it's actually negative 1 over 1 if we're thinking of this in terms of rise over run. So our slope is going to be a line in this direction here. So to graph this, we're just going to go up 1 over 1, which is the same thing as up 2 over 2, since these guys are increasing in increments of 2. So we're going to go up 2 over 2, and in this direction here, since our slope is negative. So graphing this here, and we're not going to go past this horizontal axis here, as we know that this is one of our boundaries. So plotting our points and then connecting them with this line here, this is one of our boundary lines. Now the other boundary line is going to be given by this here, so our y-intercept in this case is going to be positive 30, so it's going to be right there. Then our slope is again going to be negative, and our rise is going to be 3 or negative 3, and our run is going to be 2. Now, since we're increasing this in increments of 2 in the vertical and horizontal direction, we're going 2, 4, 6, 8, 10, and then 2, 4, 6, 8, 10. I'm going to rewrite this slope here in terms of that. So it's just easier to see what's happening with our rise over run. If our slope is negative 3 over 2, and I multiply the top and bottom by 2, this is going to give me negative 6 over 4. So this is the same thing. So that means if I want to plot some more points starting at this y-intercept here, I'm going to go down 6 units and then over 4, or in other words, down 3 and over 2 here. So down 3 and over 2, since we're again increasing by increments of 2, is going to look like this here. All right, so this point here is going to be where our two lines intersect. We're going to continue plotting some more points. Now in this region here, we're just going to go up 6 and to the left 2, so it's going to look like this here. But notice this is one of our boundary points, so we actually don't even need to plot more points here. Our line is going to look like this, and it's going to hit this point here, this 20, 0. So from here, we want to figure out where all of our solutions lie. If we go back to our original inequalities here, in green, we want to find the y values that are going to be less than or equal to this here. So that's going to be everything below this green line. Similarly, for this peach or this orange line here, we're looking at y values that are less than or equal to this guy. So this is also going to be below this line here. And then remember, we are including these values here. We have a less than or equal to symbol. So that's why these lines are solid and not dashed, to emphasize that our solutions are also going to lie on those lines. So if our solutions are going to be the intersection of these 4 lines here, that's going to be what we see in pink. So it's going to be here, then come down, and it's going to be everything in this region. Now, in order to figure out what our maximum profit is going to be and how many of each type of ring should be made daily to maximize this, so we're trying to find the max x and y values. Then we want to figure out what the maximum profit would be by plugging in these maximum x and y values. So our x and y values are going to be given by the vertices of these graphs here, or this intersection. So our first vertex is going to be this point. I'm going to circle them in pink here. So it's going to be that point 0, 24. So our vertices, the first one is going to be 0, 24. Our next one is going to be this point here. We kind of have this vertex right around here where these two lines intersect. That is going to be, since we're increasing for increments of 12, that's going to be 12, 12 here. And then our last vertex is going to be this point here, so we'll circle that guy as well. That's going to be 20, 0. So now what we need to do, so these are 3 potential solutions. What we're going to do is plug them into our profit function here to figure out what of these values, these x and y values here, will maximize the profit. So let's test our first vertex here. Our profit, if we have 0 of our VIP rings and 24 of our SST rings, plugging this in, this is going to be about $960. Now, if we had 12 of each type of ring here, we're going to plug this into our profit function and figure out how much we would make. This would give us about $840. And lastly, we want to see how much we would get if we only made 20 of our VIP rings. So this would be this here. And in this case, we would only get $600. So clearly, we're going to maximize our profit if we make 0 of the VIP rings and 24 of the SST rings. So let's write that on the side here. When x is 0 and y is 24, we're going to maximize profit at $960. So this is the most amount of money that we can make given these constraints here that we translated into these inequalities. All right, so that'll be it for this video.